Swayam Prabha. Digital India. Educated India.
I have pi r cube by 3, and we can do some simplification here. We can get 1 minus cos theta outside. In both these terms here, we have 1 minus cos theta and we have a 1 minus cos theta in both these terms. We can pull them out and we can do this, we can simplify the rest of it. And what we now have is, let me just do that. 1 minus cos theta a can be pulled out. We have 2 times 2 plus cos theta e times sin theta e minus sin theta e times 1 minus cos theta e. This whole quantity, maybe I should make a little bit of space for myself here. This quantity multiplying d theta e by d capital R. And this quantity, as we know, is equal to 0. Right? So we can straight away see some simplifications that are possible. Cancellations are possible. If I set this whole quantity to 0, then pi r square will cancel out. I have 2 r's are gone there, and what I'm left now with is 1 minus cos theta e. I can also cancel out 1 cos theta. This quantity will cancel out this with this 1 minus cos theta e. What I'm finally left with is 1 minus cos theta e times 2 plus cos theta e plus r by 3, and we can multiply, we can simplify this a little bit, and what we get is, we get 3 sin theta e plus 3 sin theta e cos theta e of d theta e by dr, and we know this quantity is equal to 0. Okay, so from this we therefore get d theta e by dr is nothing but minus of 1 minus cos theta e 2 plus cos of theta e divided by r sin theta e plus 1 plus cosine of theta e. So by imposing a volume variation in the volume to 0, we have got this d theta e by dr, which is the unknown thing in equation number 3. So let's label this. We have relationship number 4, right? So now we can actually take this is forward. We have substituting d theta e by dr from equation 4 into 3, we get, so it's a little tedious, but let me first write it down. Gamma SL minus gamma S times sine square theta plus r cos theta e sine theta e times d theta by dr. D theta by dr is nothing but minus 1 minus cos theta e times 2 plus cos theta e divided by r sin theta e 1 plus cos theta e. That's the first term in equation number 3, and then the next term would be gamma times 2 into 1 minus cos theta e plus r sin theta e d theta e by dr. So let's write that down, plus gamma times 2 into 2 times cos theta e plus r sin theta e multiplied by So this whole thing we can set it to 0. Now notice that this is a relationship that where only we have the three surface energies and the contact angle theta e and r. But if you again pay attention, this r sine theta e will cancel out here. So r has disappeared from the calculation. Disappeared from the analysis that we're doing. So what we now have is, we have the simplification as follows. So we have gamma SL minus gamma S. We have sine square of theta e minus, sorry, I made a small error here. What cancels out is not r cos theta e, what cancels out is r sine theta e. So this is r, this is what I wrote down. So r and sine theta will cancel out. So what now we have is minus cos of theta e times 1 minus cos theta e 2 plus cos theta e divided by 1 plus cos theta e. That's the first term. And then the second term is nothing but gamma times 2 into 1 minus cos theta e minus cos theta e into 2 plus cos theta e by 1 plus cos theta e. This whole thing is equal to 0, right? And so we can do a few simplifications. Multiplying throughout by 1 plus cos theta e, what we now have is gamma SL minus gamma S times 1 plus cos theta e times sine square theta e. So that is sine square theta e plus sine square theta e times cos theta e. That's the first two terms that we have here. Then we have cos theta e times 1 minus cos theta e times 2 plus cos theta e. Then on the second term would just be gamma 1 minus cos theta e times 1 plus cos theta e would just be sine square theta e. That's just 2 sine square theta e minus 1 minus cos theta e times 2 plus cos theta e. This goes to 0. This is what we have, right? We can notice that we can combine a few terms here. Let's combine these terms first. This quantity we can multiply. We can also do the same thing for the last two quantities as well. The last two quantities can also be multiplied. So let's quickly do that. So the multiplication would yield 2 cosine of theta e plus cos square of theta e plus cos cube of theta e. That's the first thing. And then finally here we would have 2 sine square of theta e minus 2 plus cosine of theta e cos square of theta e. This would be 0. Now we can combine a few terms. For example, sine square theta e plus cos square theta becomes 1. We can also combine these two terms. Here cos theta, if I take it common, I get again sine square plus cos square theta. So I'll use that relationship. So gamma SL minus gamma S the first two things sort of underlined, it's 1, so that's 1. Then I have sine square theta plus cos square theta, that's again 1. So that's again just gives me plus cosine theta. Then I have finally what's left is just 2 cosine of theta e. Over here again we can do a similar I can join a few terms here. The sine square theta e has 2 terms here. I can combine it to the last one, and therefore what's left is only sine square theta e plus 1 it survives. I have minus 2 plus cosine of theta e. This is 0, and therefore we simply have gamma SL minus gamma S of 1 minus cos of theta e plus gamma of, I have sine square theta minus 1, so that is minus of 1 minus sine square theta plus cosine of theta e is 0, and this further simplifies to plus gamma times cosine of theta e minus cosine square of theta e. If I want to consider a case where cosine of theta is not equal to 1, we simply have gamma SL minus gamma S plus gamma of cosine theta is 0, or we simply have gamma SL plus gamma cosine of theta e is gamma S. Sometimes people also write this to be the cosine of theta e tells me that the relationship between the surface energies, that is gamma S minus gamma SL by gamma, tells me the cosine of the angle. So this equation is referred to as the Young's equation. This is the Young's equation or Young's law. Okay. Now this result that we've got here is valid is valid for a much wider case than what we have just derived here. This is a very fundamental equation in capillarity. So let's quickly recap what we have seen in the lecture today. We started out by considering a partial wetting condition. We took a sessile drop on a surface. We assumed the sessile drop to be part of a spherical cap. We then wrote down the expressions for the volume and the energy of the spherical cap. Then we wrote down the total energy of the system that needs to be minimized. Then we substituted the expressions for the various areas that we have, and therefore we got the energy. We considered a variation of this energy, and we set the variation of this energy to 0, and we got this unknown quantity, which is the variation of the angle with respect to r. We impose the volume constraint now. We said if the variation in the volume is 0, which means that the volume is constant, then we can combine the two relationships, and finally we can get the Young's angle. Okay, the Young's angle or the equilibrium angle, cosine of theta e, is just simply related to the various surface energies that are present in the problem. Now what we have not done so far is to consider a situation where the drop shape is not known. Here we have used the exact shape of the droplet using geometry. What if I don't know the shape of a droplet, or it's not so straightforward? In such cases, we'll have to take a more general approach where we'll have to write down the energy in terms of an unknown height function, the height of the droplet, and then we will have to impose these boundary conditions as well, and then we'll use the Euler-Lagrange equation or the energy minimization on an auxiliary function, where we'll have to invoke the Lagrange multiplier and so on. So that's what we are going to do in the following lectures. So I'll see you around in the next lecture. Thank you.